Okay, it looks like the recording is up and ready to go, so let's get this started. Let me first kind of show you where we're at in terms of our course calendar and where we're going to be going. We've got 2 more weeks of class and the week devoted to the course assessment from DMAC left to do. This week, we're going to focus on creating statistical inference for paired data sets, paired T confidence intervals, and hypothesis testing. We'll have a quiz on this Thursday that focuses on the last 2 weeks of material, hypothesis testing for the difference in two means, and this week's focus on paired T inference. I'll get a study guide out to you guys later this afternoon. I just want to go ahead and double check it one more time and make a key for it before I get it sent out to you, so look for that if you'd like to use it as a resource to study for your next quiz. Next week, first week of May, we have one more type of statistical inference method called chi-square goodness of fit testing. We'll focus on that, plus one more quiz. Before we wrap up the course the week following, I'll spend the Monday and Wednesday classes going over the study guide for anybody who has questions, and then we'll take the test on Thursday, May 14th. If anybody cannot take the test on this day, you need to let me know as soon as possible so we can get alternate plans ready. You will not be able to take it after the 14th because I have to get grades submitted for Van Meter and DMAC. Without taking that end of course assessment, I cannot give you a DMAC credit. That needs to be done. I cannot give you a grade unless all the quizzes from second semester and that end of course assessment have been finished. So if you need to do it another day than the 14th, let me know what day you want to take it beforehand. Questions on this, guys? Once again, if there's anything you want to reassess or work ahead on, if you have quizzes that need to get made up, please be communicating with me. I'll probably send out some more reminder emails this week, later this week. All righty, let's do it. So this week's focus is on paired data sets. Standard 22 inference on paired data. So we are comparing two populations where we have two samples in which observations in one sample is paired or linked with observations in another sample. This is different than the types of questions we've been doing for the last 2 weeks, where we looked at confidence intervals and hypothesis testing for the difference in means. We were focusing on disjoint populations like men and women, juniors and seniors, two disjoint, non-overlapping different populations. And we've found hypothesis testing, confidence intervals for the differences in means from those two different populations sampled. Now we have the same population sampled twice, and I have paired data. It's like I'm picking 10 people. I'm recording some data point now. I'm recording some data point later. I want to find the confidence interval statistical inference for the differences in those two samples. So what we're going to do is create, from our two samples of paired data, we're going to create one set of sample data on the differences from those two paired data points. Create one set of data by calculating the differences between the paired data points, between the paired samples. So we're going to turn our two different sets of data into one by using the differences. Some noteworthy formulas here when it comes to confidence intervals and the test statistic for a hypothesis test. The confidence interval starts off with what D bar is here. Just like X bar is the sample mean, D bar is the average of the sample differences. D bar plus or minus the t-score times the S sub d, that's the standard deviation of the sample differences divided by the square root of n. Our t-score is found using n-1 degrees of freedom. Even though I'm sampling twice, I'm sampling the single set of people, set of samples. The test statistic is t equals d bar minus mu sub d. This is the difference for our sample minus the expected difference for our sample over the standard error, which is s sub d divided by the square root of n. If I go back here, if you haven't found this already, I've linked the spreadsheet that I'm going to use for our data sets in class today. If you click on this link where it says statistics meeting down below, there's a blue text that when you click on it will open up a copy of this spreadsheet I'm going to use. It should look something kind of like this. So if you could please open that up, we're going to use it here in class today. All right, so first up is just the data from the first tab in that spreadsheet. We'll reuse this spreadsheet again on Wednesday. It has stopping distance in feet for 10 cars. Their stopping distance for the same 10 cars was recorded twice, once on a set of dry pavement and once on a set of wet pavement. What we're going to try and find is this set of data enough evidence to suggest that wet pavement causes a change in stopping distance for a car? Once we're done with that, we'll create a 95% confidence interval for the difference in stopping distance between wet and dry pavements. Once again, I'm not sampling two different sets of car. I'm sampling the same set of cars twice, once on dry pavement and once on wet pavement. So even though it looks like I have two sets of data, in a second, we're going to create one set of data by looking at the differences between these two values, and then do a t-test on those differences. So here on Google Sheets, what I'm going to do is in the cell next to our spreadsheet, type equals dry pavement minus wet pavement. Now you could have done wet pavement minus dry pavement. You would have just gotten +6 as opposed to the -6 we got. It will not matter. You could do it either way. We'll pull down this tab. And Sheets automatically takes dry pavement minus wet pavement for each of the 10 different cars. These are the paired differences, the paired set of differences for the stopping distance between dry and wet pavement for the cars in our sample. Let's do a t-test on those differences. In order to do so, I'm going to do equals average. Let's get the statistics from these differences. What is the average difference in stopping distance? -7.2. So our estimate is that dry pavement takes 7.2 feet less to come to a complete stop than wet pavement. Let's find the standard deviation of these pair differences. 3.584. So d bar equals -7.2. S sub d equals, what was that one more time? 3.584. All right, so let's set up our hypothesis test. We're going to, in the first question here, see if this data suggests that wet pavement causes a car to change. See if is this enough evidence to suggest that wet pavement causes a car to change in stopping distance at a significance level of 5%. Is this enough evidence to suggest that wet pavement causes a change in stopping distance for a car? So let's assume that there is no difference. Therefore, there be 0 for the differences between dry pavement and wet pavement. All of these values here, when I take dry minus wet, would be 0 if there was no difference in the stopping distance for cars on dry and wet pavement. We're testing to see if it causes a change, and therefore the average stopping distance would not be equal to 0. If I draw this rejection region, we'll have a two-tailed test at the 5% significance level. So 2.5 in either tail. Going to my spreadsheet, we have a sample size of 10, so 9 degrees of freedom. And on our t-table, two-tail, 5% significance level puts us in the middle column. 9 degrees of freedom is 2.262. So if I can calculate a test statistic that's more extreme than plus or minus 2.62, we have evidence that suggests that there is a difference between stopping distances on wet and dry pavement. So our test statistic is T equals D bar divided by S sub D over the square root of N. So T equals negative 7.2 divided by 3.584 over the square root of 10. I get a test statistic of negative 6.35. So what does that tell us? Do we have significant evidence? Are we further from 0 than plus or minus 2.262? Well, certainly. Negative 6 is much further into the tail than negative 2.262. So we have significant evidence. We need to reject the null hypothesis. Evidence suggests a difference in stopping distance between wet and dry pavements. Lastly, let's find the p-value. We'll use Sheets for this again. And on Sheets, the coding is equals tdist. If you're not sure what to type in, click on this help menu. I need the test statistic, the number of degrees of freedom, and how many tails. So for our sample, our test statistic was negative 6.35. We'll type in the positive part. Sheets only wants the positive part. Degrees of freedom was 8. And we had a two-tailed test. Should be a very, very small number. 0.0002. Once again, the p-value interpretation is the probability of a sample or a sample more extreme if the null hypothesis was true. The chance that we've made a mistake, a type 1 error, we've rejected a true null hypothesis is only 2%. Or, I'm sorry, 0.02%. We've allowed ourselves a 5% significance level, a 5% chance of a type 1 error. So this is less than that. We can reject the null hypothesis. Questions so far? Okay. Next up, let's create a 95% confidence interval for the difference in stopping distance between wet and dry pavement. That formula is d bar plus or minus the margin of error, where the margin of error is our t-score times the standard error of s sub d over the square root of n. Pulling back those numbers again, we had negative 7.2. Plus or minus, let's look up that t-score. I think it's the same, but we'll look it up again. For 95% confidence interval, which is still in the middle column, at 9 degrees of freedom, gives me 2.262 for our t-score. Times our standard error of the standard deviation in our paired sample differences, which is 3.584. Over the square root of 10. Let's start simplifying this here. 2.262 times 3.584 over the square root of 10 gives me a margin of error of 2.564. All right, so our estimate of 7.2 feet less stopping distance on dry pavement rather than wet is no more than 2.564 feet away from the actual difference in stopping distance between dry and wet pavement. That's why it's the margin of error. So let's find our confidence interval by taking negative 7.2 minus this number, negative 9.764. plus the margin of error is negative 4.36, negative 4.636. And this would be in feet. In other words, we are 95% confident that on average, the difference in stopping distance between dry and wet pavement is between 9.76 feet and 764 feet and 4.636 feet less. We are 95% confident that on average, it takes between 9.764 feet and 4.636 feet less to stop on dry pavement than on wet pavement. Questions you guys have there? Rather than look at this as two different samples, I take the differences of the samples for the same 10 cars and then do inference on our singular set of data. Okay, if you go to the next tab down below on your spreadsheet, I have another set of data that focuses on the effectiveness of summer schooling. We've got 6 students who take an exam in June and then again in August after summer school. Does this results provide evidence that the summer school program is worthwhile? Worthwhile meaning that the scores in August are more than they were in June. Scores have gone up. I'm sampling the same 6 students twice in June and August. So these are paired samples. These 2 different sets of data are paired between the 6 different students. So what we can do is calculate the difference between their 2 test scores and do a t-test on those differences. So next to this spreadsheet here, I'm going to type equals. In this case, you know what? I think I'm going to do August minus June. In that way, if I get a positive score, I'll know that their scores have increased throughout summer school. So August minus June. For the student in row 1, I see that the difference is -4 because their scores actually went down over the course of the summer. As I scroll down, it'll autofill and calculate all the other differences. Student 2 did really good. They went up 16. Student 4, not a lot of change. They went down slightly. We can see all the rest of the data sets. So let's get our statistics for this sample. For our paired differences, I'll need the average for D bar. .333. I'll need the standard deviation of the differences, 7.448. When it comes to degrees of freedom, for a set of 6, I'll have 5 degrees of freedom. Okay. First up is the hypothesis test. Do these results provide evidence that the summer school program is worthwhile? Have an alpha significance level of 5%. What would the null and alternative hypotheses be? Let's assume that there is no difference first. The average difference in the student's scores is 0. Therefore, there is no difference between their scores at the beginning of the summer and at the end. Now, I want to see that the summer school program is worthwhile. Therefore, the differences when I do August minus June would be positive. Their scores have increased. If you would have done June minus August, you would have gotten negative 5.333, and you would change this to less than 0 for your alternative hypothesis. No problem there, you certainly can. You'll just have different statistics to test throughout your hypothesis test. We'll draw the rejection region. We're testing at the 5% significance level, a one-tailed test in the upper right tail. I want to make a type 1 error, reject the true null hypothesis only 5% of the time. What is that t-score that cuts off the top 5%, the other remaining 95%? On our t-table, at the 5% significance level in a one-tailed test, we're in the second column from the left. For 5 degrees of freedom, I see a t-score of 2.015. If we can calculate a test statistic that's more extreme than 2.015, I have evidence that backs up my claim that the summer school program is worthwhile, that students' scores have increased. All right, so let's get this set up. Our test statistic, t equals d bar divided by s sub d over the square root of n. The average of the paired differences divided by the standard error, which is the standard deviation of the paired differences over the square root of the sample size n. So we had 5.333 over 7.448 divided by the square root of 6. See, that was 7.448. All right, I get a t-score of 1.754. 1.754. Let's look back at our rejection region. Where would 1.754 be? Is it in the rejection region or not? 1.754 is to the left of 2.015. It's not more extreme. So we lack significant results. In other words, we fail to reject the null hypothesis. We lack evidence to show the summer school program is worthwhile in increasing student exam scores. Lastly, let's get the p-value. Back on our sheets, we'll need equals t-dist. Our t-score was 1.754. We had 5 degrees of freedom and only one tail this time for our t-test. And I get a p-value of 0.0699. When I compare our p-value back to our significance level, it's outside the window of our adjusted error, our allotted error. So we cannot reject the true null hypothesis. We cannot reject the null hypothesis. Any questions there? Okay. Part 2, let's look at the confidence interval next. Confidence interval is the average of the sample differences plus or minus the margin of error, which is some t-score, times the standard error of S sub d over the square root of n. Going back to our data here, our sample differences had an average of 5.333. Plus or minus, let's look up our t-score. It is going to be different again because now I need a two-tailed t-score for our confidence interval. 95% puts us in the middle column as opposed to the one next to it for the hypothesis test. For 5 degrees of freedom, I see a t-score of 2.571. 2.571. Times the standard deviation of the pair of differences, 7.448. Over the square root of 6. All right, so let's plug in our margin of error first. It's 2.571 times 7.448 divided by the square root of 6. Gives me a margin of error of 7.817. So our estimate shows that student scores increase by 5.33%. Our margin of error means that we are no more than 7.817% away from the true average increase for all students. So let's get our confidence interval. 5.333 minus the margin of error gives me negative 2.484. I add the margin of error. 13.150. This would be in percents. Meaning we are 95% confident that student scores on average are between 2.484% lower to 13.15% higher at the end of summer school than the beginning. Because 0 is in this interval, we are not sure that summer school is effective. We are not sure that there's a difference in scores at the beginning when compared to the end, which is why in the hypothesis test, we failed to reject in the first place. On our first example, our confidence interval was strictly negative. 0 is not in the interval. So our data shows that there is a difference. Dry pavement takes shorter length to stop at, which is why we rejected the null hypothesis in that hypothesis test earlier. Questions there, guys? Okay, if there are no questions, I will get a study guide for Thursday's quiz out to you sometime this afternoon, and hope to be in touch about anybody who needs to get any work made up sooner rather than later. When it comes to the end of course assessment here in a couple weeks, if you do know already that you cannot take it on that Thursday and need to do it earlier, let me know of what time works best for you and we can move forward from there. Okay? Otherwise, have a good afternoon, and we'll see you guys again on Wednesday.